Okay, so well, welcome to the Astrophysics weekly Astrophysics seminar. And first, I want to thank OFEC for the great job in organizing it. So it will run from today at least until the end of the semester. As far as I could see, we're pretty much booked. Pretty much every week. I think we even have some double bookings, and we have to shift and play around. So it's as you know, it is these are very exciting times in astronomy and astrophysics in general. And don't need to say, OFEC said it in his great colloquium that was given earlier this week about the Nobel Prize. And very many exciting things are happening in astrophysics currently and in the last few years, and of course in the coming years. And as of today, we're very pleased and we're very honored to have with us Shmuel Bialy from Harvard. Shmuel. Shmuel did his PhD about 3 years ago, right, in 2018, in Tel Aviv University, working with Amiel Sternberg. And the thesis title, as I have it, is Atomic and Molecular Interstellar Gas Processes Across Cosmic Times. From there, he moved to Harvard. He's now an ITC, Institute for Theory and Computation fellow at Harvard University. And he's there since 2018. As a student, I see that you got several awards. The most notable one that I could see is the Dan David Award, the Prize Fellowship, which you got a few years ago. So thank you very much for being with us, and I'm looking forward to hearing you.
Thank you for this kind of introduction, Asaf, and thank you for inviting me to talk here. And I see so many people, and that's young people also, and it's good to see this, and also to talk about general astrophysics in this group. Let me start with sharing my screen, and you tell me if you see it, okay? So, do you see my screen?
Yes, okay.
Yeah.
Yes.
All right. Okay. So today I want to talk about something maybe new to some of you, maybe not. And that's about how stars form in the interstellar medium of galaxies. First of all, I want to also thank my collaborators at Harvard and worldwide that made this possible. So what I want to talk about is how stars form in the interstellar medium of galaxies across cosmic times, from early cosmic times until today. But before I dive into the topic of star formation and the interstellar medium, let me first back off a little bit and talk about the large context. So one of the basic questions we'd like to ask in astrophysics is, how did the universe evolve from the state of almost homogeneous density here? Of course, you had some fluctuations, the CMB, but it's very minute fluctuations. Most of it was homogeneous, into the state of highly inhomogeneous universe filled with these magnificent structures, galaxies, different kinds. Some are star-forming spirals, and some are quiescent, large elliptical galaxies, within which we have stars and planets and humans, apparently. So that's the basic question we'd like to ask in the galaxy evolution and star formation field. But let me introduce some basic observations. Of course, I cannot now cover the whole field, but I'll just mention few important observations that are relevant for this talk. So the first plot I'm showing here, this is the so-called Hartmann-Dau plot, showing the cosmic star formation, the cosmic star formation rate in the universe as a function of redshift or cosmic age here at the top. And what we see here is that at higher redshifts, at early cosmic times, the star formation rate was low, and then it was increasing towards redshift of 2, at which point it peaks, and that's what we call the cosmic noon. And since then, since redshift of 2, at a cosmic age of 4 gigayears, some 10 gigayears ago, since then, it was steadily decreasing until today. Why is that? A clue may be given from the gas fraction in galaxies. So these are observations of the CO molecule in different galaxies, star-forming galaxies at different epochs, redshift here at the bottom. And what we can see that while today the molecular gas fraction in galaxies is quite low, so less than a 0.1%, at early cosmic times it was high. So the reservoir of star formation, that's the gas, was much more abundant in early cosmic times. Of course, you can then ask, why was that? And that's a good question. But this is already the first clue. This makes the connection between gas content and star formation, which will come back later in this talk. By the way, if you have any questions, feel free to interrupt if it's pressing and something is not clear. Okay. Then the metallicity.
Sorry, what is Z, the x-axis?
That's the redshift. That's a measure of time here, like here, redshift, that's Z.
Okay.
So it's a redshift of the galaxies. That's, you can think of higher Z is just meaning more into the past. Okay. Okay, so here again, the redshift. This is early cosmic times, that's today. And here in the y-axis, I show the metallicity. That's the abundance of heavy elements. Specifically, this is metals. And this is actually a very important parameter in astrophysics because we know that at the Big Bang, everything was produced just with hydrogen and helium. And then the universe got enriched in all the other elements, including carbon, oxygen, metals, everything we know from the synthesis in the cores of stars. So with time, we expect the increase of these elements. And indeed, we see that as we go from early cosmic times here till today, there was a steady increase in the metallicity. So we call this the metallicity. A steady increase in the metallicity in galaxies. In fact, this is observation not of galaxy. This is called DLAs, damped Lyman alpha systems. These are gas systems that are seen in absorption towards quasars, in which we see these metals. They are thought to be part of the interstellar medium of galaxies or the circumgalactic medium around galaxies. So this is from the observational point of view. Now, what do we know from theoretical point of view? So until quite recently, the main route of studying the evolution of the universe was using n-body simulations. These simulations tell us how the gravitational field, especially of dark matter, evolves with time. And they show that the gravitational interactions result in the so-called cosmic web. So that's the collapse of structures into halos, but not only halos, also filaments and disks. Sorry, not disks, filaments and sheets. And in the interactions of these filaments, you find the most densest part, and that's where we think galaxies form. But now within the last decade or so, the computational power has increased enough so that we are now able to not only simulate n-body interactions of gravity, but also the magnetohydrodynamics of the gas, of the baryonic matter, non-dark matter. And here I show as zoom in into one of the state-of-the-art simulations, Illustris. Now we have Illustris TNG, the next generation. In this simulation, in this movie, we see now the gas temperature, the gas density, the metallicity. This is the metallicity. So these simulations follow the magnetohydrodynamic equations following the collapse of gas into these structures, the galaxies. And this is very heavy simulations that are run on millions of CPU hours worldwide and involve very large collaborations. And the reason is because they really simulate the universe, dark matter, and also the gaseous interactions from early cosmic times until today. And this is an example of a formed galaxy in one of those simulations. So they are amazing, but there is a problem. And the problem is that because they simulate such huge volumes, cosmological volumes, and they include so many galaxies within them and dark matter interactions and everything, they cannot go and resolve the small scales, meaning the structure within the galaxies. They get the galaxies in few pixels. And that's a problem. That's a problem because the stars are forming inside galaxies. Oh, can we just mute this? Thank you. The stars are forming inside galaxies. Specifically, they form in molecular clouds inside galaxies. So if we want to really have a good understanding of star formation and the galaxy evolution, we need to be able to resolve these scales, but that's not possible because computationally that's too expensive. So what these simulations do, they have models. It's called subgrid models. These are like prescriptions or recipes that tell the simulation how much stars to form, how much energy to input from the stars back into the galaxy, onto the interstellar medium. These recipes tell what's the ISM, what's the structure of the interstellar medium. By the way, when I say ISM as the interstellar medium, what's the structure of the ISM? Is it homogeneous or porous? What's the density? And this feedback is also very important because it tells you how much energy and momentum is injected back from the forming stars and supernova that follow. All these things, the star formation, feedback, they affect in the end how the galaxy would look like. What's the star formation rate, what we saw before the first plot, what's the star formation rate in the universe, what's the metallicity, what's the molecular fractions of galaxies. In fact, they even affect things that seem to be unrelated, like dark matter and the cosmological evolution of the universe as a whole. Because, for example, the structure of the galaxy include not just the baryonic matter, but also the dark matter. And then people go ahead and use these simulations to study the structure of the dark matter to deduce some properties on the dark matter. For example, if it's cold dark matter or theories of warm dark matter and things like this. But these are also affected by these subgrid models of star formation and feedback. As of cosmology,
Sorry, can I ask you a question here?
Sure.
I thought you mentioned that the galaxy is not really resolved in these simulations. The large-scale simulations, the galaxy is only a few pixels.
Well, wasn't generous enough. It's not few pixels. They are resolved, but not enough to resolve these star formation sites, the molecular clouds. It's not few pixels. It's more than that.
But cannot you simply use the outcome of these simulations and then do a different simulation for the specific galaxies, looking at the star formation at that under this?
No, that's an excellent point. And actually, many people do that, and that's called zoom-in simulation. So they use the simulation, and then they take one of these galaxies, and then they make another simulation and zoom in. This is what you meant?
Yes.
Yeah. So this is a good approach if you want to take the big-scale simulations and to study star formation with realistic initial conditions, like cosmological initial conditions. However, if you want to draw statistical conclusions, so to take the simulation and use the power of statistics that you have so many galaxies with different properties, then that won't help you, right? Because this will give you one galaxy or few galaxies that you did the simulation on. You'd really need to do it on on very large sample of, say, million galaxies in the simulation, which is again unrealistic. That's one thing. And the second, this doesn't include back reaction because the galaxies, the formation of stars within galaxies also affect the entire evolution because the stars then inject feedback back onto the galaxy and sometimes resist the accretion of new matter onto the galaxy. And this you won't get it if you just make a new simulation on top.
If most of the accretion is due to dark matter, that will not affect it, right?
Right. At some point on large enough scales, I agree. But the feedback may be very large scale because also, for example, they have AGN feedback from active galactic nuclei in the black holes in the center of the galaxy, and how much the black hole accretes matter within the galaxy, and how much energy and momentum does it induce back onto the circumgalactic medium. This you cannot resolve, and this you have to model, and this will affect everything because AGN feedback is large scale.
Thank you.
So it's not just the dark matter accretion. This affects large scales as well. And the second point is the radiation, because the structure of the interstellar medium in galaxies then dictates how much of the ionizing radiation is able to escape from the galaxy. And this radiation is the one that reionizes the universe as a whole. So all the study of universe reionization in cosmology and all the study depends on this parameter, how much ionizing radiation escapes, which depends on the structure of the galaxy. So these models are very important for all these things. However, the current model used in the state-of-the-art simulations, specifically Illustris TNG, which we saw, is very simple. It just assumes that there are two phases, neutral and ionized, and the neutral phase forms stars with some epsilon efficiency that is a parameter tuned to observations today. So it's a very simple model, which, as I'll argue, doesn't capture most of the physics. That's one motivation, I think, a very strong motivation for studying star formation for the large scales and also these other fields, dark matter and ionization. However, of course, I have interest in this just because of I find it interesting by its own. And this is because the interstellar medium and star formation, it's really an opportunity to study and to explore so many different physics, because it really involves so many different kinds of physics coming together that we need to understand star formation. This includes turbulence. So as you will see, turbulence in the ISM is very important. So turbulence is a big question in physics generally. So we get to study this from different directions of the ISM. Atomic physics, when we want to understand cooling and heating, which is also crucial for gravitational collapse and star formation. And chemistry, because in the end, all the observations we have of the ISM is of different molecules and atoms, so we need to be able to model them properly. So that's actually a field, astrochemistry. So in this talk, I'd like to ask several questions and try to shed some light on them. And the first one, and maybe most important one, what is it that regulates star formation in galaxies? So I mentioned already turbulence, but as we'll see, the UV radiation and cosmic rays play also an important role in regulating star formation, as they are able to heat the gas and resist star formation. Then if we know that turbulence and UV radiation and cosmic rays are important, we may ask, what is it that drives the turbulence in the ISM? Why do we have turbulence at all in the ISM? What are the properties of these cosmic rays? And what's the structure of the ISM of our galaxy and other galaxies? I had the chance to work on all these questions during my PhD and postdoc, but today I'll focus just on the first question here, what regulates star formation in galaxies? And then I'll describe projects relating to the other questions in more briefly. This first question, what regulates star formation, we can put it in a different way using the very well-known famous observation called the Kennicutt-Schmidt relation, or the star formation law of galaxies. And this plot shows you on the x-axis each point here is a galaxy or a part of a galaxy. These are observations that resolve galaxies, so these are nearby galaxies. The telescope beam is smaller than the entire galaxy. And in each telescope beam, people have measured the surface density, so of gas, and the surface density of star formation. And this is what's shown here. So we have the surface or column density of gas versus column density of star formation. And what we see that there's this nonlinear trend, but generally there is a relation between the two. And it's not surprising because the gas is what fuels the formation of stars. Now, an important thing to look at here is to divide these two quantities. So if you divide sigma, this sigma gas, the gas column density, by sigma SFR. By the way, SFR throughout the talk, star formation rate. SF is star formation. So if you divide the sigma gas by sigma SFR, you get a time scale, right? They have the same units, except that this is per unit time. This is star formation rate. And this time scale is called the depletion time here. This time scale tells you how much time, given the star formation rate observed and the amount of gas observed, how much time would it take for this galaxy to consume all its gas into stars? Of course, it's just an approximation. In the end, it doesn't do that, but it just gives you kind of a time scale for the star formation on large scales of the galaxies, right? What we get.
What's the color coding?
Oh, these are different kinds of galaxies. So for example, these are starburst galaxies that are known to be very bright and very effective in forming stars. And these are some other local galaxies. And so just in different papers, yeah, you shouldn't pay too much attention into these color codings. And what you can see is that these are lines of constant depletion time. And you see that the numbers are of order giga-year, billion years. And in fact, most of the galaxies lie here with the depletion time of 2 giga-years. So that's the time scale. And we'd like to compare it with another time scale we know. And what is it? This is the so-called free fall time. How much time would it take for gravity if you just leave it alone? How much time does it take for a cloud to collapse until a small radius where star forming? And when you estimate a free fall time for these galaxies, you get something of order of 10 mega years. So that's much shorter. This means that it is not forming stars with a free fall time. It is much slower. So something is slowing down the star formation by about a factor of 100. That's what people refer to as the star formation is inefficient, or has an efficiency of about 1%. So there's something that is more than gravity that is at play, that is dominating star formation. That's why I mentioned here these other processes and did not write gravity, because it's not the gravity that dictates the star formation rate. It's something else, and that's what we'll see. Okay, so I'll focus on this. So let's dive right in, and let me start with a small introduction of the ISM. So the ISM, as we know it from observations of our galaxy and also nearby galaxies, it's also, as the universe is, it's also highly inhomogeneous. So the density of the ISM varies by much, and also the temperature. This is a cartoon I made for this talk that I think depicts quite nicely what's happening. So you have most of the volume is filled with rather diffuse gas that is warm. That's called the WNM, warm neutral medium, of a density less than 1 particle per cc. So that would be more vacuum than any vacuum in lab on Earth. So that's the warm neutral medium, and the hot ionized medium is even more diffuse than this, even less dense. And this is also ionized and have temperatures of million or 10 or 100 million degrees. That most of the volume is filled with this diffuse gas. Then you have smaller volumes that are filled with cold neutral gas with the densities of, say, 50 particles per cc. And the temperature is about 100 Kelvin or less. And by the way, small fractions of the volume are filled with this cold neutral medium, but in terms of mass, it may be half of the mass in this cold neutral medium. It's very compact. And the cold neutral medium is the place where we see then, this is the Hubble Space Telescope image, a very well-known image of what's called the pillars of creation, where we see here dark, cold molecular clouds, very dusty, full of dust. And these are the sites that collapse with gravity to form stars. These are the star formation sites. And they occur within the CNM, within the cold neutral medium. So we really need to understand why is the ISM composed of these phases, the CNM and WNM, and what's their proportion, and what regulates their abundances, if we want to understand star formation. So why the ISM is composed of these phases? Why isn't it just, single phase? Why do we have this, what we call a multi-phase ISM composed of warm and cold neutral medium? I focus here on the neutral medium because that's where most of the mass is, and that's where stars are forming.
Last slide.
So actually, yeah.
In last slide, you mentioned something transonic turbulence and.
Oh, right. Sorry, I forgot to mention this also. Yeah. So also the observations of various atomic and molecular lines, they show that the widths, from looking at the widths of the lines, they show that the gas is actually very turbulent, and in the case of the cold neutral medium, it's supersonic turbulence. So the Mach number, the sonic Mach number, is much larger than 1. In the case of warm neutral medium, it's transonic. So the sonic Mach number is around unity. And this is also very important because for the CNM, the supersonic turbulence, we know it's a compressional turbulence. So it produces very strong density fluctuations in the gas. So the CNM itself is also very inhomogeneous with, with most of the volume, again, filled with less dense material, and then some clumps that are much denser. And these might be the clumps that then in the end form these, nice molecular clouds that later form stars. So turbulence will play a role in the later stage of CNM compressing into molecular clouds and forming stars.
Yep.
Thank you for the reminder. So the multi-phase ISM. So the first and basic question, this is actually a classical question that was asked already by Field et al. And Zeldovich in 1969. Why is this multi-phase? And can you explain this, from first principles? And it turns out you can. And the idea is, if you just consider what are the heating and cooling processes that are at play in the ISM, you may obtain the multi-phase behavior. And what are they? So for heating, it's basically photons and cosmic rays. Photons, what they do, you get a UV photon, far UV photon, that heats a dust grain. It heats a dust grain. The ISM is very dusty. There's a lot of dust, or the universe as a whole. FUV photon hits a dust grain, elaborates an energetic electron from the dust. It's a photoelectric, like the photoelectric effect. And this energetic electron then thermalizes with the gas and heats the gas. That's the photoelectric heating from UV and dust. Then you also have ionization heating, where more energetic photons, X-rays, and also cosmic rays, which are not photons but energetic particles, penetrate throughout the ISM, ionize hydrogen, molecular hydrogen, ionize it, and again, the electron that is escaping is energetic, and then it's thermalized in the gas and produces heating. As we'll see, also H2 heating may also play a role, but let's leave it for now. Then for the cooling part, it's always collisional excitation followed by radiative decay. So what's happening is you have two particles, and then you have some temperature in the gas. Two particles hit each other, and now instead of bouncing back, this energy goes into excitation of one of the electronic levels or vibrational or rotational levels of molecules. And this excitation then decays back into the ground state, emitting a photon that escapes the system and thus cools the system. So that's the cooling mechanism. And depending on temperature, there are different agents that do that. For example, at high temperatures of about 10 to the 4 Kelvin, It's Lyman alpha cooling. That's the N equals 1 transition of hydrogen. For lower temperatures of about 50 or 100 Kelvin, it's fine structure transitions of C plus and O neutral oxygen. And then there's also molecular cooling. But basically, it's always this process of collision excitation and radiative decay. And now the final thing that that we have to remember is that because the cooling is a collisional process, so it involves two partners in the gas, it goes as the density squared. The rate of cooling goes as density squared, whereas heating involves gas particle and the photon or a cosmic ray, so it goes as the density of gas to the power of 1. Why is that important? Because this means that as you increase the density of the ISM, the cooling rate increases compared to the heating rate, and therefore you expect the temperature to go down. And that's what we see here in this plot. So this plot, this shows the thermal steady state, meaning if you take all the heating processes, and I listed these, but there's even more than this, and all the cooling processes, again, there's more than this, and equate the two. And now as a function of the density of the ISM, solve the cooling equals heating equation, you get the thermal steady state temperature. And this is how it looks. First, it's stuck at one temperature of about 10 to the 4 Kelvin. Then after some critical point, it starts falling down, and then it falls down to about 50 Kelvin. And why is it stuck at 50 Kelvin or at 10 to the 4 Kelvin? That also has an explanation. This has to do again with the atomic physics. This is simply the equivalent temperature of these transitions, of the line separation of this fine structure transition. So that's given from quantum mechanics. That's the energy level separation in temperature units. So that's how it looks like.
But
and
isn't that shouldn't that be strongly dependent on the type of galaxy that you're looking at?
Exactly. Excellent question. That's the next point. This is not just one universal curve. It depends on parameters. And the basic parameters that I show here, this is the metallicity, the UV intensity, and the cosmic ray ionization rate. Now these parameters are basic physical parameters, but they may be related to galaxies. So one galaxy, let's say a galaxy at the early universe, or a galaxy that is very small and very small, like a dwarf galaxy, will have a different metallicity than a massive galaxy like the Milky Way. Or a starburst galaxy that is forming stars like crazy will have a high IUV and high cosmic ray ionization rate, high these parameters. So these curves depend on these parameters, and these parameters are tracked back to the galaxy type and the cosmic epoch. And this is in fact what we did new in this paper from Bialy and Sternberg in 2019, because I told you this is a classical problem, but what we considered as these variations with these parameters that are related to different galaxies. And as you'll see, I'll show you in a moment, there are surprising things that happen as you change these parameters. But this is the basic idea, the one WNM and CNM.
Now, in this plot, or the previous plot, is it a coincidence that the phase transition or the red point is precisely at n equals 1 in units of cubic centimeters?
Yeah. It's a coincidence. If you choose a different value for Z here, IUV or zeta, you get a different number. Yeah, as you'll see.
And do these numbers change in orders of magnitude, or just between 1/2?
They are quite often proportional to these parameters, as we'll see. For example, the proportional to IUV, and so these can change by orders of magnitude. Not many orders of magnitude, by few, and so these can go to 10 or 100. Yes. So now what I did here, I take the same plot, this plot, and instead of showing T here in the y-axis, I just multiply T by K Boltzmann N, or actually just by N, to get the pressure, assuming ideal gas, which is a good assumption. So this is the thermal pressure now as function of N. So there's no new information here. It's just a different way to show it. But why do I do it? There's a good reason to do it. And because the pressure now, the pressure parameter may be thought of something that is set externally by the galaxy. For example, if you have a disk galaxy that is pushing from above and from below, like here, if we just go outside, we have the pressure of atmosphere on our head, or if you go diving, then you have a higher pressure. So this is set by the hydrostatic equilibrium of the disk galaxy. So this gives you the y-axis. So for a given galaxy, you get a pressure. And then you can ask the question, given the galaxy and the pressure I calculated, what's the state of my ISM? Is it cold? Is it warm? And what we see here is a very interesting thing. Indeed, if the pressure is very low, let's say 10 to the 3, you look at this plot and you get, okay, the density is 10 to the minus 1 and the temperature is 10 to the 4. This is the WNM. The entire interstellar medium would be warm, and that's it. If the pressure is very high, let's say 10 to the 5 in these units, then you look and you see, okay, actually, I'll have an interstellar medium that is pure CNM, 50 Kelvin, and a density of 10 to the 3. But there is a pressure range between few 10 to the 3 and almost 10 to the 4, where if the pressure of the galaxy falls here, you draw this line and you see, wait, this goes through the WNM and CNM and this in the middle branch. What does it mean? It means that at this pressure, let's say 4,000, both solutions, both the WNM and CNM are steady state solutions. So you can have ISM that is warm or cold. Both solutions will satisfy the heating cooling equations. So what will happen? So what happens naturally, and this is also shown by hydrodynamic simulations, that the ISM separates into a state where it's multi-phase. So most of the volume of the gas is warm and diffuse, within which you have clumps of cold neutral medium, of dense and cold gas. And this is a stable situation. And in fact, this is very similar. There's a nice analogy with an example we know from our life, and this is water. So when we boil water, there's a point. Of course, it's just an analogy because it's not the same thing, but there is a point when it gets to the boiling point where we have liquid and gas coexisting at the same temperature, 100 degrees Celsius. And this is also a steady state. And only when we increase and continue to pump in energy, then we go to full gaseous state, or if we decrease, we go to full liquid state. And this was already pointed out by Zeldovich at this paper that I mentioned. And there is a very interesting analogy with this.
Can I ask you a question about that?
Yeah.
So the pressure, of course, is expected to vary as a location along the galaxy, right? The further you are away from the center, it varies.
That's true, yes.
Is one thing. So, and the second is I would expect to see some strong fluctuations of the pressure different locations, even at the same radii of the galaxy.
True.
It depends on whether you're talking about spiral galaxies, for example, when you're close to the arms or not. So my question is, in that plot, roughly, can you tell what would be the fluctuations in the pressure that you expect to see?
Right. No, this is an excellent point. And in fact, both observations and simulations show this. So this would be kind of to guide, the kind of average behavior. And in a second, in a few slides, I'll show also a simulation where we'll see these fluctuations as we just talked about. That comes from just the turbulent nature of the, because I said it's turbulent, right? So and also everything is true, both the radial and also there is spiral arms and non-spiral arms. And even if you have the same conditions, you have the turbulence that in some regions produces some higher pressures and some regions less pressure. So all is true, and we'll see in a moment an example, okay? Okay, so far, this discussion is just a theoretical discussion. This is just a discussion of the solutions of these heating cooling equations at some physical parameters here. Now you can ask, okay, so what observations tell us? And the remarkable thing is that indeed, when we look at observations, there are observations of atomic carbon with UV lines that gives you a handle on the pressure in the ISM. And indeed, there is a distribution, as you set us up. But the mean and the median pressures that are found for observation, they fall here. This is the median pressure in the ISM as obtained from atomic carbon UV lines. And indeed, it falls very nicely within this multi-phase range. So given the pressure observations, we do expect to get a multi-phase ISM. On the other hand, there's also another set of observations, and that's atomic carbon via the 21 centimeter radial line, which also give us information on what's the density of atomic hydrogen. And this also, and density and the temperature. And this also, from another point of view, constrained that the ISM is multi-phase. So from two kinds of observations, both 21 centimeter of atomic hydrogen and carbon lines, we do get the information that the ISM is multi-phase, and this is in agreement with the basic theory from first principles. And I'll get into your question, Asaf, in a second. I didn't forget about the fluctuations, but before I wanted to introduce the idea of self-regulation by UV heating. So this is very nice and to know that the ISM is multi-phase, but one can ask, okay, is it just this? Are there any implications to this? Why is it important for star formation? And it turns out it might be very important for star formation. It might be actually a natural regulation process for star formation. And here's how. So what I showed so far, this curve, is the equilibrium, is a steady state cooling heating for a given set of parameters, right? We had these Z metallicity, UV radiation intensity, and cosmic ray ionization rate. These are the three basic parameters. Now, what happens if we change these parameters? If we increase IUV by a factor of 10, it means we increase the heating rate, because we said that heating is from photoelectric heating, this photoelectric effect. So what happens, you increase the heating rate by a factor of 10, how do you deal with that? You still want to get steady state. Cooling is more effective at higher densities. So what happens, your curve shifts to higher densities to compensate for the increase in heating. So this is IUV of 1 and this is IUV of 10. And it looks like this in the pressure density plane. So the curve goes up and to the right. Now, this is the basic idea for self-regulation by star formation. Because here how it goes. Let's say you had an ISM, a healthy ISM, multi-phase with WNM and CNM, like in our galaxy, like in the Milky Way. So let's say the pressure, the thermal pressure is 4,000 in these units, and you have a multi-phase ISM. Now, let's say for some reason you increase the star formation by a factor of 10. Now your curve is no longer this blue-red curve, it's now the magenta curve, this one. You look at this curve and you ask, okay, the pressure didn't change, so you're still here, and you ask, what's the state of the ISM? Is it multi-phase? No. Now it's pure WNM. So everything is warm. Now stars do not form in WNM. The WNM, the warm neutral medium, is diffuse and warm. It's stable against star formation. It's stable against gravitational collapse and star formation. So you stop forming stars. You stop forming stars, you stop producing UV radiation. The UV radiation is coming from young, massive stars. You stop producing UV radiation, UV goes down until you're back to the original configuration. And you can walk out the opposite direction as well. That's the idea of regulation by UV heating and this multi-phase ISM. So just to say it in other words, P is determined by external things like the disk weight, and there's other things that can also determine the pressure. Given pressure that is externally determined, the multi-phase is regulated to be more, the ISM is regulated to be a multi-phase. That's only then you get a star formation. if it's multi-phase, it means that UV is proportional, the pressure is proportional to the UV. So you have this, and you can connect all these steps and you get a relationship between the star formation rate and the gas density. So the gas density here. And this is what we saw before, the Kennicutt-Schmidt relation, the star formation relation, which is kind of the basic cornerstones of star formation in the field. So that's how you get a star formation law naturally from this multi-phase behavior and the heating and cooling balance. And this was noted already before, many years ago, by Paravano and Yves Ostreicher and Chris McKee, and formulated. Now, before I move on, are there any questions on that? Okay, so that was one way of regulating star formation. However, recently, with the understanding that the ISM is highly turbulent and
Wait, I have a question.
Yes.
Sorry.
Yes.
You showed us that there is some regulation against different UV luminosities.
Mm-hmm.
What about the other three parameters that you have there, such as the metallicity?
Right. So here, for example, for the cosmic ionization rate, here we assume they are proportional because cosmic rays.
Proportional.
Yeah. So because cosmic rays, but this is actually also a good, point for a new research, because this is actually very, very unexplored. But the basic, very rough idea is cosmic rays. Here we're talking about low energy cosmic rays. These cosmic rays are produced in the supernova remnants, thought to be produced in supernova remnants. This is one of the acceleration mechanisms for cosmic rays. And the supernova rate is proportional to the star formation rate. Same as the UV radiation field is also proportional to the star formation rate. It's all the very massive stars that produce the supernova and also the UV radiation and the cosmic rays. That's the.
I doubt if it's going to be linear. There will be some power.
No, I agree. I think this is, and actually this is, I talked about this with many people in the field, and this is a very good project, I think, that I plan on doing. This is unexplored.
Okay. What about metallicity?
And metallicity we'll see in a second. Yeah, this is for metallicity of solar, like in our galaxy, but as you'll see in few slides, there's also interesting behavior on metallicity. The reason I start with the UV, because the UV is connected to the star formation rate directly, and this gives you a regulation process. Now, this regulation process will depend on the other parameters, of course, as you say, but the basic first thing I think to discuss is the UV. And we'll see the metallicity in a second, okay? And that's actually the focus of our paper here, Bialy and Shmuel in 2019, where we studied different metallicities, thinking of first galaxies in the early universe. What was the situation back then? But before then, I'll have to shortly introduce also the alternative theory, and that has to do with supernova and turbulence. And you'll see why I talk about this, because the idea is it was noted that the star forming stars, they also, in the end, the massive ones, go supernova. And the supernova is very energetic, and it is thought that this is one of the main mechanisms that produce turbulence in the gas. Observations in the ISM, in other galaxies, suggest that the ISM is turbulent so much that, in fact, the pressure that you get from the turbulence, if you like, rho sigma squared or rho v squared, the pressure that you get from turbulence is larger than the thermal pressure. So the argument is that everything I said here, that the thermal pressure here balances the disk, is irrelevant, because the claim is that the disk weight is balanced by turbulent pressure and not by thermal pressure. And then the regulation mechanism by supernova would be that if you increase the star formation rate too much here, you produce too much supernova. The supernova induces too much momentum into the gas, puffing up the disk, reducing the density, and so reducing star formation. And then it goes reducing star formation, reducing back the supernova, and then the disk can collapse back and become dense and start forming. So there's a kind of a debate in the community. Which one is it? Is it the thermal pressure and this mechanism of UV that we discussed, or is it from a momentum injection from supernova? You can view it as, is it momentum or energy? Because here it's the energy that hits the gas and prevents the formation of cold phase. And here it's the momentum that puffs up the disk and prevents the formation of stars. So it's either, is it momentum or is it energy that regulates star formation? And each one of these regulating mechanisms will give you a different star formation or different dependence on, say, metallicity and other parameters. So that's a debate which I'd like to try and answer. I think part of the answer may lie here in this relationship between the UV and star formation rate. By the way, how am I with time? Should I be accurate or should I not be accurate?
How much longer do you need?
I think maybe I'll be 10 minutes late.
That's okay.
Okay. Because I just wanted to discuss a recent project that I just finished that was just accepted that has to do with this connection between the UV and star formation rate. Because why is it so important? Because which one is it? Which one is more important? Which of the mechanism depends on how, for a given star formation rate here, how much pressure you get, how much turbulent pressure versus how much thermal pressure. Which one is higher? And the relationship between the star formation rate and UV is critical. If you, for a given star formation rate, how much UV you get? Do you get a lot of UV or less? Will determine which one is higher, P thermal, P turbulent, and therefore which mechanism dominates. So this is what I want to talk about now. So this is a question I recently looked into in here in the paper that was just accepted to UpJ. So the question is how much UV you get for a given star formation rate. And you can approach this from two directions, either numerical or theoretical or analytic theoretical. And I did both. So let me start with the numerical. Numerically, you can just think of a simple calculation where you take a disk as a galaxy and you place different sources. What are the far UV sources? These are stellar associations of massive OB stars. Now these stars, they usually go in associations and not alone. The complication is each association may have higher mass or lower mass, higher luminosity or lower luminosity. There's no one single value for the luminosity of association. That's why you see here different points of different sizes. Some are more luminous and some are less. And then you place the observer somewhere in the disk, in the center or off center, and go ahead and just draw lines and calculate the flux from each of the sources to this point. However, you have to take also into account dust absorption because the galaxy is dusty, and so you have to e to the minus tau absorption by dust. So this is what I did here. And actually I did it 10,000 times because you can have different realization of these sources. They have different luminosities and they can have different locations within the disk. So you run it 10,000 times, you try to place them in different locations, and each time you calculate and you get a distribution of UV radiation field. And this also depends on the parameters of the galaxy also, again, the metallicity which comes into the dust absorption, right? If they're more metal rich, you have more dust and you have more absorption of radiation. If they're less, then it's less. And also the gas density, which also comes into the dust absorption. And as we'll see in some cases, also the galactic radius also is important. So this is from a numerical point of view. From an analytical point of view, actually, if it was just uniform, if all associations had the same luminosity and you place the observer exactly in the center of exponential disk, then you can actually walk out and solve this analytically because you just start integration from some point, assume that the sources are continuous instead of point sources, and you get an integral of just e to the minus tau divided by r squared times r dr d theta. And this is solvable. This is the first exponential function. And this is what we see here, the first exponential function. But the problem is, of course, what I mentioned before, that the sources are not the same luminosity, and the observer may be not in the center, and then you don't have the polar symmetry that you had in the original problem. And I worked this out. This is all in my paper from 2020, which you can find also, I can send you. So I think this is a very interesting derivation. But in the end, what I get is an analytic solution for this ratio UV to star formation rate as a function of the galactic properties. Now, these galactic properties, there's many galactic properties that are relevant that I mentioned here, like the metallicity, gas density, galactic radius. But in the end, if you analyze it, you find that there is just two dimensionless important parameters. And they can be written like this, tau star. Tau star is the dust opacity between two nearby sources for the typical distance between sources. And in physical units, it's about 0.4. So it's exactly in the interesting regime where it's not optically thin and not optically thick. And the second is dimensionless galactic radius, which is the ratio of the galactic radius and the typical distance between sources. And this is about 8 or so for a galaxy like our Milky Way. So these are the two basic dimensionless parameters upon which everything depends. By the way, x naught is just a number, and this encapsulates all the difficulties that I told you about with the associations having different luminosities and things like this. So we have this analytic model now. Now let's look at how it looks like when we plot it. So this is the analytic model. This is, by the way, the numerical results when I compare the two. And they're actually in very good agreement of within 10% or so for most of the parameter space. So here we have these two parameters, tau star and x. And maybe more easier to look at the more physical and parameters that we know better. This is the scale radius, the galactic radius, if you like, and the dust to gas ratio or metallicity. It's kind of their proportional. That's by the way another very good project. What's the relationship between dust to gas, between dust abundance and the metals in the gas? But never mind. For now, let's think of it as just the metallicity. So here you have high metallicities. So this is conditions like the Milky Way, like our own galaxy. And if you go to low metallicities, this would be conditions like in high redshift, early universe galaxies, and also dwarf galaxies that we see today. So these would be different kinds of galaxies. And as you see, if you start from Milky Way conditions where you have UV to star formation rate equals 1, well, they're normalized to Milky Way values by default. And then you decrease the metallicity, go toward higher redshift universe about first stars, then you increase the UV to star formation rate ratio by factors of u. And in fact, this is for a central observer. If the observer is not in the center, it can be even higher than this. And this can be also intuitively understood because you have less dust, so you have less absorption. So in Milky Way conditions, you do not get radiation from all the stars in the disk. Instead, you just get a small circle within which you are affected, because larger than this, dust absorption just kills off the radiation. And as you decrease the metallicity and the dust abundance, you're exposed to more and more stars in the galaxy, until finally, when you cross this line, the entire galaxy become optically thin, and then you see all the stars. In this case, the radiation field is independent of the dust abundance and become only dependent on the second parameter, the scale radius. So larger galaxies, you have more stars, and then you get more radiation. So that's the two regimes here, the regime limited by dust absorption here, and the regime where UV is limited by the galactic radius.
What is the dimensionless galactic radius?
So that's the ratio of the galactic disk size and the typical separation between two radiation sources,
Okay.
which is about 100. This is about 100 parsec L star. The typical separation is about 100 parsec, and the galactic radius, this is galactic radius of OB stellar associations. So for our Milky Way, it's like 3.5 kiloparsecs.
So you're assuming that the galaxy is like a box with
No, it's I assume exponential. I assume exponential, the exponential disk.
Okay.
Not a box, but infinite exponential.
Okay.
So that's the picture. And for our story, why is it important for our story? Again, to remind you, this ratio, how much UV you produce for a given star formation rate, this is what we wanted. This is what we have here. What we see that for a galaxy, for metal pool galaxies like high redshift galaxies or dwarf galaxies, this ratio may become high by a factor of 3 or 4, or in some cases even 5. So while the classical theory or the recently it was suggested that P-turb is higher, now what I'm saying is that given this analysis, this would dominate in high redshift and low metallicity galaxies, whereas this is dominating in galaxy like our own Milky Way. So the question, which one is it, depends on metallicity. Finally, just a final word about metallicity, and that's also answering the previous question that you asked, Ofek, is except from the relationship from the UV and star formation rate that we saw here, also the phases themselves, the phase diagram also depends on metallicity. And this is this plot is showing the phase diagram for different metallicities. So this is what we saw before, the black line. Now, what happens if you decrease the metallicity? You decrease the UV heating rate. And at some point, at a metallicity of about 10 to the minus 2 or so 1% of the solar, UV heating rate becomes so low that cosmic ray heating from other sources like cosmic rays and X-rays, which I mentioned before, become more important. And at this point, what happens if you further decrease the metallicity? You decrease the cooling rate, because cooling is by C plus and O. So you have to go, as we saw for the UV, if you decrease the metallicity, you need also to go to higher densities, because you decrease the cooling, you have to compensate with higher densities. So this is what happens if you go from metallicity of 1% to 0.1%. So this would mean that even more so, the thermal pressure would be more important than the turbulent pressure, and also would mean that the star formation rate would be less, the star formation efficiency would be lower at low metallicity galaxies, at first galaxies. And finally, it's also very interesting that we find that at super low metallicities of this 10 to the minus 4, you totally lose this multi-phase behavior, and you get this continuous curve, this purple curve. And I don't have time to explain this now, but this has to do with the cooling and heating by a molecular hydrogen. That is a different kind of a coolant mechanism. So at first galaxies, this suggests that there should be even a totally different regulation process for star formation. So just to summarize all these points together, we've seen that star formation may be self-regulated by the multi-phase ISM, with this idea of the UV going up and everything becomes warm and then goes down again. Then I told you about other competing theories. And now after this analysis of the UV to star formation rate and also the dependence on metallicity of the phases, I think the conclusion is that the mechanism that regulates star formation may be indeed supernova or UV heating or cosmic ray heating, depending on the conditions, on the metallicity, and so the kind of galaxies, either dwarf galaxy or high redshift galaxy or first galaxies. However, we still need to put this all together into one unified theory, and that's what I'm working on now. And also to test this with simulations, because this is, of course, very idealized models that do not take into account many complications that there are. And I just wanted to show you some preliminary results with a collaborator of mine. This is a hydrodynamic simulation where you have a stratified disk. So it's kind of infinite in the z direction, but is boundary conditions that are repeated boundary condition on the x and y directions. And then you have here the hydrodynamics of the gas, and you also have stars that are forming when the gas becomes high enough. There's these are these points that you see, and then there's prescription for the supernova that goes slightly after the star is formed, in some cases, depending on the observed observations. And this launches momentum and energy. And here you see the distribution of temperature at the lower panel that you can see here indeed that at about 100 Kelvin, you see the CNM, and about 10 to the 4, you see the WNM, and that's the rest, the ionized gas that we also discussed in the first slide. So we want to use this kind of simulations, but with different varying conditions like metallicity and disk size and dark matter to study this from a numerical simulation point of view and to compare with the model. That's the plan. Finally, this analytic model of IUV to star formation rate is also very important for interpreting extragalactic observations, because the state of the gas, the molecular, how much molecules you have, for example, how much CO do you have or H2, depends on the UV radiation field. So this would also help interpreting extragalactic observations that are coming soon with JWST. All right, so I just wanted to come back to this initial slide we had. I mostly talked about this, but I just wanted to mention some other projects that I've been working on, and also how do they relate to the future, the other future directions other than what I just mentioned about the regulation of star formation. And these are 4 other projects that I've been working on. I'll just cover them in 2 minutes and then I'll finish. So one is what I call the TurboChem method. So I didn't have much time to talk about turbulence, a little bit, but there are many open questions in the field of interstellar turbulence. And here I've been working on several papers to develop a new method to constrain the properties of turbulence in the interstellar medium using observations of different molecular and atomic species. Then the cosmic rays, which we also discussed, there are many open questions in what is the cosmic ray ionization rate in the galaxy. And specifically, we have very bad understanding of the spectrum of cosmic rays at low energies because they cannot reach Earth because of the solar wind. So we don't know the spectrum there. And there are very indirect ways to constrain these cosmic rays, although they're very important for star formation. And recently I proposed a new way to use molecular hydrogen line, looking at very dark clouds and searching for infrared lines which will constrain the cosmic ray rate. You can ask me about this and I'll explain. But basically, we are now, I just proposed an observational program and we got 3 nights, and another 2 that were canceled because of COVID. So we got 3 nights and observations are coming in 1 month, and we're expecting to be the first to detect these lines from dark clouds like this one. This has never been done before. The third thing is the ISM. Until now, all observations of galaxies and the interstellar medium has been done in 2 dimensions. So you look at the sky and you see something and you analyze. Sometimes you have the velocity, the spectrum, but you never hope for a 3-dimensional picture. Only in simulations you have 3-dimensional. Now this is not a simulation. This is a real 3-dimensional image of a nearby molecular cloud, the Perseus molecular cloud. This has been possible thanks to Gaia, that has very accurate measurements of stars, which were then used to produce 3-dimensional dust maps of the distribution of dust from the absorption of this. From the absorption of the radiation from stars, we could infer the 3-dimensional distribution of dust and form these 3-dimensional maps of nearby clouds nearby ISM, and we are using these maps to study the ISM in 3D. And for example, we find that some of the nearby clouds, very known clouds, may have formed from compression by supernova. That would be the opposite side, positive feedback from supernova instead of negative. That's a work in progress.
How much time is represented in that not simulation?
How much what?
Time, real time.
What do you mean? How much time? They do not rotate. It's not really rotation.
Oh, it's just a display of a 3D.
Yeah, it's a display. Yeah. They rotate, but it will take much longer than this. Yeah. No, this is a display of the same cloud, just looking from different directions. Now you can imagine that if you see it in 3D, you can learn many new stuff, and that's what I mentioned, that known clouds that we just thought that are unrelated, now we think they're part of a huge supernova bubble that produces them, because now we can see it from different directions. This is not what you see here. This is, but I'm telling you this offline, because this is under taboo. So, and the final thing is, I mentioned the subgrid models for the cosmological simulations, and this specifically the one that is used in Illustrious TNG, the big collaboration, that are not that are missing important physics, specifically those that we just went through: the UV heating, the turbulence, the cosmic rays. So I'm working now with Lars Hengwist and others here at Harvard to build a new model for future simulations of galaxy formation and cosmological simulations to be used as subgrid models for star formation. And I'm slightly over time, but I hope that's fine with you. That's it. I'll be happy to take more questions. Thanks.
Thank you very much.
In this image of interstellar turbulence in the top left,
Yes.
we expect the interstellar turbulence to be having morphological similarity with the kind of turbulence we see in the gases in laboratory, where the large eddies form and then they dissipate into smaller eddies.
Yeah, that's an excellent point, and that's indeed what we see in the simulations, and also infer from observations that the turbulence is cascading from large scales to small. From the injection scale, which is actually an open question, what injects the turbulence? Is it, for example, on quite small scale like stellar winds or outflows from stars, or is it on the large scales of the galactic disk itself from the gravitational interactions of the galaxy? But whatever it is, it cascades from the large scale to very small scales where it is dissipated into heat.
And what's the time scale of typical time scale of this dissipation?
Oh, the time scale of dissipation, or yeah. So I'd say I think it's about a mega year. Yeah. So I know the large scale is mega year, but it then has to be kind of equilibrium, that the dissipation injection scale should be in equilibrium. Otherwise, you get energy or lose energy. And these are, by the way, the plot that is shown here. These are slices through an MHD simulation box where you drive turbulence continuously. And this shows the density field in log scale. So blue is low and red is high. And the idea is that these density fluctuations, they affect the abundance of different molecules, like molecular hydrogen and CO and other molecules, because the molecules are very sensitive to the density. And then when you observe the molecules from the fluctuations you see in the molecules, you can infer back what's the density field and what's the properties of the turbulence. That's the idea of this TurboChem method.
Do we constrain the Reynolds number associated with this turbulence?
Yeah, so that's actually a problem, because the simulations can never reach the Reynolds number in nature. In the real ISM are very, very high, because the systems are very large, and the Reynolds number are of order like 10 to the 6, 7, 8 in the ISM. And the simulations never have a resolution that is even close to that. So that's a problem we always have in this field of turbulence, simulating turbulence in the ISM.
Okay, thank you.
Any more questions? If not, let's thank the speaker again.
Thank you very much.
Thank you.
We cannot
Thank
invite you for dinner or lunch.
Yeah, actually,
Next time you're around.
Asaf, I don't know, but I might. Yeah, we